back to the second half of this session. Right now we have Ali Zifan from right here at UCSD, who's going to be talking about high resolution manometry and some of the differences, high definition manometry, and some of the differences between normal and fecal incontinent individuals.
Good afternoon. First, I'd like to talk about the detail of So actually, this discussion, I mean, first when I joined cosmetology group a couple of years ago, 3 years ago to be exact, I was not very involved within the, now. So recently we had a little escapade into the pelvic floor. So what I'm going to discuss today, I think it's the modality of high definition manometry. It seems like it has been overlooked. And actually this is probably in line with Henrietta's actually talk. And it's like, what actually, what modality is there, the instrumentation is there. What features could we actually extract from this modality? That's just probably, as most of you know, like FI is a loss of involuntary liquid as well as stools. And it's a very embarrassing and debilitating symptom. It poses like public health problems. And there have been like different studies showing different prevalences between men and women, like 8 to 1, or another one by Rowe, prevalence of 1% to 7% healthy, up to 25% institutionalized. As for the etiology, it could be congenital, anatomical, neurological, and functional. But today the topic will be mainly focused on the functional testing. And right now the gold standard for performing this kind of test is the anorectal manometry. So it's a critical test. It measures the pressure of the sphincter muscles. It measures the sensation of stooling and the reflexes that govern bowel movements in the rectum and the anus. Now, so nowadays there are like different kind of catheters from different companies for the high resolution and high definition, having different sensor array kind of placements of like given imaging and Sandhill, like A, B, and C, like cell catheters for doing high resolution manometry. And there is one from given imaging for performing, which has actually a matrix of 16 by 16 electrodes on the catheter. So the question is, 2D or 3D? Why do we care? Will we get any extra kind of information using 3D? So, does high resolution manometry, does it provide detailed information on the circumferential and axial symmetry? So, okay, it provides dynamic pressure information. But what about, the structural, indirect structural information? So that's where high definition anorectal manometry comes in. It's relatively novel, overlooked, but it allows access to regional pressure distributions along the length and the circumference of the esophagus. However, as we heard from our fellow colleagues, there is no consensus as to how to best analyze. This is where we come in. So we're going to introduce some simplistic, physiologically palpable kind of features that you guys can extract from these images. So the goal is to how do we extract local robust and global features from this high definition anorectal manometry data. After all, what the probe is measuring is a rate of some musculature around it, right? So, and could we develop and evaluate a prediction model actually for fecal incontinence that could robustly differentiate normals from patients using statistical learning? So for the study subjects, we recruited 24 nulliparous women in age 39 plus minus 10 years. For the FI, the mean was 58 plus minus 13. They had a mean physics score, the fecal incontinence severity index of 35, plus minus 11. Mean. So extracting features. What kind of features? I mean, so there's a plethora, like, of features, like whether it's like just simple first order, second order, like, that you actually like, from an image processing kind of perspective, you could extract from any image. But like, are they physiologically meaningful? I mean, the first one, I mean, if you see on the upper image, it's the uninterpolated sensor of a typical patient breast, left lateral. Okay, so as you can see, during squeeze, you have an increase in pressure solution. So the thing that comes to mind, now, if you look at this as an elevation map, where elevation corresponds to pressure, and do the same thing for squeeze. So, peak pressure could be a good feature, could be extracted. That's the first, so peak pressure. The second, you have a rest, you have a squeeze. On each, you have a peak, okay? So how much does this peak move? So the second one, displacement, okay? So peak pressure, displacement. And the third one is the high pressure zone area, okay? So if you have, this is an interpolated, like, image of a resting person. And now, if you use a contouring algorithm to extract the isocontours. Isocontours are lines of similar intensity of this image. And then you get a segmentation method, and you can apply different thresholding, and you get an approximate boundary of the HVZ. Combining the former two, you get this picture D, now choosing the isocontour line that encompasses the blue region. Actually, you can get the high pressure zone region automatically. And actually, you can use it as a mask on the original image. So the fourth region, I think the most important, which I think is symmetry. How do you define symmetry? Now, assume you have a square, and you have to build, like, reflect it horizontally. Now, if you subtract the two, you'll get a 0, because it's perfectly symmetric horizontally, right? Now, if you have a square with irregular shapes within it, and do the same thing, but vertically, this time, the subtraction will not be 0. So that's in simple terms. Now, going back to so now imagine if you have a binary image, the red is 1, the rest is 0, and if you flip it, you get the image in the center, you subtract it, you get a bunch of zeros. Now you can do this actually to an actual SDAM, and actually the numbers are the intensity of the pressures, so to get a feel. Now if you flip it horizontally, and now we insert subtraction, we call this the anorectal symmetry index. Right now you can use a mean of it, or different, You could do actually the same thing with the same image, but it's only taking into account the shape. So you got the first image on the left, flip it horizontally, and subtract it, and you could do this actually vertically too. And for our study, we just use the mean of both vertical and horizontal, but you're free to choose, either. So we applied these features on our database. So figure A, you can see the x-axis is the 24 normals at rest, B is at squeeze. You can see the same thing for the patient population, as you can clearly see, they don't have substantial increase in pressures at squeeze. So this is a typical HDAM image of a normal person cut in the anterior line at rest, A, and then squeeze. You can get the same thing for a patient. So they are on the same scale. So actually visually, you can see the differences among the two groups. In terms of peak pressure, for normals, they had a median rest of 99 mercury, and this went up to 279, which was significant. For the patients, median was much lower at 14. The increase was also lower at 58. So the darker blue are the normals, the cyan are the patients. In terms of reflective symmetry, I'm just going to talk about the binary one, at rest. So imagine if you have reflective symmetry. So the maximum value that you can obtain is 0. That's perfect symmetry of a circle. Now if you just only have like 2 rotation angles, either horizontal or vertical, a square could be symmetric in that sense. So a symmetry of 0 corresponds to a perfect symmetry. So at rest, the normal group have a symmetry of minus 0.46, and it seems that during squeeze, actually, they become more symmetric. So, but this was not the case for the patient group, and actually the increase was not even that the statistic was significant. In terms of area, you had a 12.3 at rest, centimeters squared, so a 15.21. And for the patients, you have a 12.51 to a 13.7, so you have a greater increase in the area actually in the normal group. The displacement. Now, you have 24 normals, you have 24 patients. Now you register them all to one axis, and you get a composite, like, you want to see what the normals look like a PDM, like a point distribution model of normals versus patients. So A and B, actually, this is all done like, we developed our own source code. This is all done within the lab. So you can see A is the mean of the normals at rest. The folded and the unfolded, this anorectal thing. And the patients, C and D, rest and squeeze, as you can clearly see. You can see even visually the variation between the two groups. In terms of classification, we use discriminant analysis and logistic regression. I can, talk more about, but I don't want to do that. I don't want to make it too technical. And we use like the area under the curve to assess the classification results. Don't be scared, just a simple table. I'm just gonna focus on the last row. So what this means, it means that if you have if I use pressure, so an area, an ASI, if I use all the parameters, and if I use logistic regression, I get a perfect classification, right? Or if I just use the ASI, I also get a good classification, just focusing on the symmetry of the HDM. Now, you can actually visualize a 5-parameter, so I just bring it in 2D, just using 2. The first one you can see, x-axis is the peak squeeze versus the area. So the normal group are shown in red triangles. So actually, does a pretty good job of separating the data. Or you could use the peak pressure versus the ASI. You get a different kind of scatter matrix, but again, good results. Or you can use peak squeeze versus displacement. And this is one last thing, just for you guys to take home. So rest or squeeze. So you see the deformation in the patients is nearly minimal. Thank you. That was it.
Hello. Thank you very much. That's a wonderful lecture. Thank you. Before I open up the floor, I do have one question, Andrew. I hope you don't mind. That the patient population that you studied seemed to have actually global, very poor anal function, and that poor global sphincter function would have been demonstrated on traditional or just regular high-resolution manometry. What additional benefit in terms of diagnostic accuracy can you attain by using this 3D technique? Because I could see there were lots of difference between your patients and your volunteers, but have you been able to tease out those who would have had normal sphincter function with other techniques and any other changes in sphincter function that you can see with the 3D probe?
That's an excellent question. Also, actually, we had a similar question raised for some of the reviews. So the question is, I mean, the population that we have, it wasn't an ideal population. So, but there was this actually interesting paper. I can just say, based on the population that we studied, this was a pressure for that figure. Just going to get in the group, but there was a paper I found in different college actually with a group in France. Then they say that almost 1/3 of the people who show up with FI symptoms, they show normal pressure. So it would be interesting to see.
Well, actually, I think in most studies it's a bit more than that, actually. Usually you find sphincteric dysfunction in about 40% of patients with incontinence.
And so it would be really interesting to test this methodology on a different population. With, with as a closer on age-matched population with similar pressure.
Yeah, thank you.
Very good question.
Any questions from the floor? Oh.
It's a mathematical problem he's trying to solve. And the thing is, the groups that we chose are not the ideal groups. We didn't have a good control. In our control, the 35 patients are 55. They are nulliparous versus they are paras. So I think when we have a better control, we're going to find that there is an overlap in the pressures. But then will be the real test, whether these other parameters, do they bring in some additional value?
What influence morphology itself rather than just pressure change? How influences?
Groundwork for other parameters that can be extracted from this category.
I think that's a challenge. Anyone else from the floor? Any other questions? No? Okay. Well, then I think it's time to move on to our next speaker. Thank you very much, Annie.